All right, just like a lot of things that we're taking a look at here in Calc 3, it had a Calc 1 correlation with it. So today we're going to go back and look at extrema, maxes and mins. So in 2 dimensions, we had some curve like this. We were trying to find the maximums and minimums, a place where it was either higher or lower than any other spot on the curve, at least in a nice little relative neighborhood around it. We want to do the same thing now, but instead of looking at a 2-dimensional curve, how do we deal with this in 3 dimensions? Well, let's take a look at a Calc 1 problem from start to finish, a real easy one. So again, this is just Calc 1. If I said, find all the extrema and classify. All right, so, and I don't know, let's do f of x is equal to x to the 4th minus 8x squared. All right, so remember how we did this. To find maxes or mins, we decided to look at where the tangent line was equal to 0. So what we did is we took the derivative, so we found f prime of x, which in this case would be 4x cubed minus 16x. Then we wanted to know where this was equal to 0 or where it was undefined. So here we'd have 4x cubed minus, what is that, 16. X is equal to 0. Here we can factor out a 4x, and that's x squared minus 4 is equal to 0, which, squeezing it down here at the bottom, you can see we have 0 and plus or minus 2. This is never undefined, so we don't have that case for this particular example. So here we have 3 possible places where we might have an extreme point. Now, a lot of textbooks go and classify these as something called a critical point. Now, a critical point is anywhere that the first derivative is equal to 0 undefined and exists in the original function. Of course, it can't be an extrema if it doesn't exist. That's kind of their clarification on that. So one way that you might have learned this in Calc 1 was to put all these values on the number line and check the value of the derivative for some test points along the way. So you may have picked points like -3, -1, 1, and I don't know, 3. You would have plugged it into the first derivative to see if it was positive or negative. So it'd be negative, positive. So over here, this would be negative, positive, negative. In this case, it would have looked something like this if you would have done it that way. And you could have seen that here, since it's decreasing and increasing and -2 exist on the graph, that this would be a minimum. Since it's increasing to decreasing and it exists, that would be a max. Same idea here, that would be a minimum. So that's one way that you could have justified saying that those were extreme points and they were maxes or minimums. But there was something else you may have learned there, something called the second derivative test. The idea for a second derivative test, if we know that something's a critical point, which means the derivative is equal to 0 or undefined there, we could actually check the concavity to tell if it was a maximum or a minimum. Like this point right here, if we were to plug that into the second derivative, we would get that the function was concave down there, which means that that would have to be a maximum if the concavity was negative. So another way to do this is if we found f double prime. Well, here's our derivative. So the second derivative would be 12x squared minus 16. Now, if we were to plug these values in now, our critical points, like f double prime at -2, that'd be 12 times -2 squared. So that's 12 times 4 minus 16. Well, that's positive, right? That's really all I care, which means it's concave up. Well, if something's concave up, that means that point right there would have to be on the bottom, which would be a minimum. Same thing if we plug 0 in here, that's really easy to see. That'd be -16. That means it's concave down, which means it would have to be a maximum. Well, we're going to do something close to this here in Calc 3. So now we're going to go to Calc 3, and how do we do the same idea? Ooh, messy. Well, we're going to do a lot of the same things that we did in Calc 1. So, finding we still need to find our critical points. Now, critical points occur where? All right, well, in Calc 1, we found critical points by looking at the first derivative. Unfortunately now, when we're looking at three-dimensional stuff, like z is equal to function x and y, we have two first derivatives, so we have to take that into account. So these will occur where f sub x and f sub y is equal to 0. They both have to be 0, or where f sub x or f sub y are undefined. Okay, so you still have to do the same thing you did in Calc 1. You got to look where the first derivative is equal to 0 and where it's undefined. Here's the difference though. With our first derivatives, when they're equal to 0, we got to find where they're both equal to 0. So we have a small little system to solve here. And we also have to look at where they are undefined. Now in this case, it's any place that either one or the other is undefined will be a critical point. Now, to be a critical point, of course, it has to exist on the the function. Okay, so there's our critical points. But once we have our critical points, how are we going to tell whether they're mins or maxes, or is there something else that can happen? Well, it's obvious to see, and I'm going to go back to some of the basic shapes we've used all semester. If we have kind of a dome like this, you can see that that could have a maximum, or if this was turned upside down, that would be a minimum. But there's actually something quite weird that can happen here. Let's see if I can screw this picture up too much. Let's see. We can have something that looks kind of like this. Sorry about the picture. This is called a saddle. You know this thing, a saddle on a horse. A saddle actually has a spot on it that's both a minimum and a maximum at the exact same time. Think about in a saddle about where your butt would go, right about there. If you look in, say, this direction, think about kind of a parabola going over there, that's the top, and then goes over the back, it would be a maximum point. However, if you look in the other direction, kind of front to back of the horse, that would still be parabola, but would be a minimum. So here we can have three types of extrema. We can have maximums, we can have minimums, and we can also have a new type of extrema called a saddle point. So in this case, we're going to be looking for three of them. How are we going to do this? Well, we're going to do something called the second partials test. So just like we used the second derivative in Calc 1, or we could use the second derivative in Calc 1, determine whether or not something's a minimum or maximum, we're going to do the same thing here in Calc 3. It's a little bit more complicated. Now, if we have f is a function of x and y, that means there's two first derivatives, which means there's four second derivatives. So we got to find a way to combine those in a way that it makes sense. We're going to define this value. You can use any letter that you want. I'm going to use D because I'm pretty sure your book uses D here. D is going to be the determinant of a 2 by 2 matrices, which is defined like this. F sub xx, F sub xy, F sub yx, and F sub yy. Which means if you actually do that determinant, that's F sub xx, F sub yy, minus. Now, since these mixed partials are the same, I don't care which one you write it as, I'm just going to call it the same thing. I'm going to call it f sub xy. You could call it f sub yx squared. So there's the value of D. All right, let's take a look at what can happen here. Let's start out with this. Let's say that D is greater than 0. Well, what would have to happen here for D to be greater than 0? Well, that means, of course, this value is positive, which means this thing is bigger than this because we're subtracting it. Since we're squaring, it's always positive. It also means that this first piece has to be a positive value. Well, if this is a positive value, that means that they both have to be the same sign. So either f sub xx and f sub yy are both positive, or they're both negative. So to reason that out, all I gotta do is look at one of them, because I know they gotta be the same if this is positive. So most textbooks here, I think, look at f sub xx, but it really doesn't matter. You can look at either one. If d is greater than 0 and, I guess I'll do what your book does, f sub xx is, let's say, greater than 0, that means the concavity solely in the x direction and in the y direction is negative. So if you looked at the concavity in the x direction, it looked like that. In the y direction, kind of going over the back and over this way, would also be concave down. Which means, since it's concave, I'm sorry, I said greater than 0 here. Concave up and concave up, right? So if that's greater than 0 means concave up. That means it's concave up in the x direction, concave up in the y direction, which means whatever point we're looking at, that would have to be a minimum. Now, same reasoning, the second kind of case that can happen, if d is greater than 0, and either f sub xx or f sub yy is less than 0, that means f sub xx and f sub yy are both negative. That means they're both concave down. So the first picture I drew over here, just turn that upside down. That means that we're looking at a maximum. And the last case that we can look at is if d is less than 0. Now there's two different ways that d can be less than 0. This ends up being positive, but this over here is bigger, which means it would end up being negative, or if one's positive here and one's negative. So another way to think about it, kind of from the picture I drew a second ago, if one is positive and one's negative, we end up with that kind of saddle picture that I had from before. It looks like that, and that would be going to the back side of it. Right, so one would be positive, one would be negative. So if d is less than 0, we actually get a saddle point from this test. Now the other cases would be if these were either both positive or both negative, but this was bigger. You can kind of think about that as kind of like the saddle would be twisted, not directly along the x and y axis. It would be in some kind of off axis, which is where the slope would be. Now, so what we're going to do is we're going to have to find this value d for each and every critical number, and this is how we're going to test what it is. So let's actually, let's go over here and try one. Let's say, find all Extrema. Now the good news is this is basically just going to be a straightforward test. Let's see, let's do negative x cubed plus 4xy minus 2y squared plus 1. Now, I'm not going to lie to you, I stole this example out of a textbook. It might actually be in your textbook, just so the numbers aren't so ridiculous, because I just make this stuff off the top of my head. I just wanted something that would work out fairly well. All right, the first thing we want to do is, find all of our critical points. So we need to figure out where f sub x and f sub y are equal to 0 first. So first off, f sub x would be negative 3x squared plus 4y, and f sub y would be 4x minus 4y. And of course, f sub x or f sub y are never undefined, right? If we take a look at these are never undefined, so we don't have to worry about this. But I do want to know where these two are equal to 0. So I'm trying to solve this system of equations where 3x squared plus 4y is equal to 0, and where 4x minus 4y is equal to 0. All right, most of the time this is going to be a nonlinear system and not particularly easy to solve. Substitution is a nice method that works out a lot. If I take this equation over here, it should be easier to see that if you solve that, you can get one statement, x equals y. And if I come back over here and replace whichever one, I get something like 3x squared plus 4x is equal to 0. I can factor out an x now, and I get 3x plus 4 is equal to 0. So I get two values, 3x plus 4 is equal to 0, so x is 4/3. So you see I get two x values, which means there's two possibilities or two places to where I probably have an extreme point. So what 2 points do I have? What are my critical points? Well, one is if x is 0. If x is 0, according to the other equation, y is also 0. And a quick check, does that point exist in the original function? It does, so it's a critical point. The other one was 4/3, comma, well, if x is 4/3, according to the other equation, y has to also be 4/3. Okay, so that point, a quick check, I don't know what it is, but you can plug it in there and get a number out. So both of these are critical points, which means I expect them to be a minimum, maximum, or a saddle point. So what we need to do now is come up with our value d. Okay, so notice for d here, I need f sub x, f sub x, y, x, and y. So let's start. F sub x. The derivative of this with respect to x is negative 6x. F sub xy, the derivative of this with respect to y would be 4. F sub yx, the derivative of this with respect to x would be 4 also. And f sub yy, the derivative of this with respect to y is negative 4. All right, so this ends up being, it's going to be 24x minus 16. So there's our function d. So all we got to do is figure out what this value is for these three cases, and we're going to see in a second, possibly a fourth. Okay, so let's plug this in. So if I evaluate that at my first point, 0, 0, that's 24 times 0 minus 16, right? Everywhere there's an x, I put a 0. Everywhere there's a y, I put a 0. I get negative 16. Okay, well, that's the d is less than 0 case, so you're basically done. So we know at 0, 0, it is a saddle point. So there's one of our extrema. All right, if we evaluate this at x is 4/3, y is 4/3, I get 24 times 4/3 minus 16, which is going to be, let's see, 3 goes into 24 8 times, that's 32 minus 16, which is 16 again. Okay, now in this case, our d is positive, so we're in case 1 or case 2. So now we got to look at, I'm going to put kind of a line here. So now let's take a look at either f sub xx or f sub yy. F sub xx is negative 6x. F sub xx evaluated at our point, 4/3, 4/3, will be negative 6 times 4/3, which is negative 8. So our second derivative, f sub xx, is also less than 0. So here we have d less than 0, f sub xx less than 0. So at 4/3, 4/3, this is a maximum. Okay, so now we found what the second point is here. Now notice f sub yy was also negative, which would have given us the same result. So technically here it doesn't matter which one of those you look at. All right, so we found all the extrema of our original function. Now notice I left off here one kind of weird case. We've taken a look when d was greater than 0, less than 0, but we never looked at when d was actually equal to 0. Of course, this is bad news because this is inconclusive. It means it tells you absolutely nothing. If you end up getting d equals 0, you're just going to have to examine the shape of the graph on its own. Sketch it real quick, take a look at, maybe some of the XY traces to get a basic idea what the graph is, and you're going to have to tell from that whether or not that's a minimum or a maximum or a saddle point from the picture. Unfortunately, we do get an inconclusive case, but it doesn't show up that often unless the shape itself is a very, very simple shape. All right, so you need to know the second partials test. It is just kind of a memorization thing. Once you run it through the test, you'll be able to tell if a critical point is a min, max, or a saddle point.